Swayam Prabha. Digital India. Educated India.
We will continue discussing the kinetics of a system of particles. In this lecture, I will discuss problems based on what we have discussed in the past two lectures. This is a problem from the book of Merriam and Craig. This says the system of three particles has the indicated masses, velocities and external force as shown. Determine Rg, Rg is the position vector of the center of mass, drg dt, this is the velocity of the center of mass, d2rg dt square is the acceleration of the center of mass, capital T is the kinetic energy of the system, capital H naught vector is the angular momentum of this system about O, and d dt of capital H naught, which is the rate of change of angular momentum of the system about O. First, we find out the center of mass. This is the definition of the center of mass, location of the center of mass. Rg is the position vector of the center of mass, and it is given by summation of mi ri by summation of mi, and if you just plug in the values and the vectors, you are going to get the position of the center of mass. Then we find out the velocity of the center of mass. We just differentiate this position vector of the center of mass with respect to time. Ri dots will give you they are basically the velocities of the particles. So, Ri dot is the velocity of the ith particle, and these are all specified. We will just express them as vector quantities and plug in into the expression of Rg dot, and we obtain the velocity of the center of mass. Acceleration of the center of mass is governed by generalized Newton's second law. So, mass times acceleration of the center of mass is equal to the net force acting on the system, and from there we will obtain the acceleration of center of mass as 1 over m f k cap. Here f vector f is in the k cap direction. Kinetic energy of the whole system, it is summation of kinetic energy of kinetic energies of individual particles. So, half m I v I square, and this is summed over, and if you do that summation, the total kinetic energy turns out to be 13 m v square. Let us look at the decomposition of kinetic energy. This we have discussed in a previous lecture. To decompose, as we have noted that the kinetic energy, net kinetic energy of a system of particles is composed of the kinetic energy of the center of mass with the whole mass concentrated there, plus the kinetic energy of the system of these particles about the center of mass because of their motion about the center of mass. So, that constitutes the net kinetic energy of the system. So, one thing is the kinetic energy of translation of center of mass, the other is kinetic energy due to rotation of the system about the center of mass, and that total kinetic energy is 13 m v square, which we have calculated using the kinetic energies of the individual particles. Therefore, the first term here is the kinetic energy of translation, the second term is known as the kinetic energy of rotation about the center of mass. So, the kinetic energy of translation, which is half m velocity of the center of mass square, can be obtained easily because we have already found the velocity of center of mass r g dot, and just substituting there in this expression we have the kinetic energy because of the motion of center of mass, and the kinetic energy because of the motion of particles about the center of mass can be found by subtracting. So, this turns out the translational kinetic energy turns out to be 4 m v square, the total kinetic energy is 13 m v square. So, therefore, the difference is 9 m v square, that must be the kinetic energy due to the motion of the particles about the center of mass. But I can also define and calculate this kinetic energy of motion due to the motion of particles relative to the center of mass using this expression, our original expression, and using the expression of rho I dot as velocity of the ith particle minus velocity of center of mass. We can do this calculation both ways. Now, the angular momentum about O, which is the origin of the coordinate system, is the summation of r I cross m I v I. We can plug in all these expressions. R i's are these position vectors of the various particles are known, the velocities are known, masses are known. If you do that, then the angular momentum about the origin turns out to be this expression. We are going to look at the rate of change of the angular momentum from the moment about O. Now, we are using that dynamical equation. The rate of change of angular momentum about O is equal to the moment of all forces about O, and that turns out to be the position vector, a convenient point where the force is acting. So, that is d I cap cross f k cap. F k cap is the force vector. So, that turns out to be minus d f j cap. So, that is the rate of change of angular momentum of the system about O. Let us look at the decomposition of angular momentum which we had discussed. Therefore, the angular momentum about O can be decomposed as the angular momentum of the center of mass about O. So, basically is the moment of linear momentum of the center of mass with all the mass concentrated there about O, plus the moment of linear momentum, relative linear momentum of all particles about G. This rho I is the vector from G to the ith particle, and rho I dot is the relative velocity of the ith particle with respect to the center of mass velocity. Therefore, this is h G, and this total angular momentum about O we have derived earlier. Therefore, we can find out first the angular momentum or the moment of linear momentum of the motion of center of mass with respect to O, and that is given by r G. R G is the position vector of the center of mass cross m r G dot is the linear momentum of the center of mass with the total mass concentrated there. And when you plug in these position vector of the center of mass and the velocity of the center of mass that we have derived earlier in this expression, we get this as the first term on the right hand side of the angular momentum about O. So, that is equal to this expression, and therefore, this from here I can calculate the relative angular momentum or the angular momentum about G. You remember that angular momentum about g of the system is same as the relative angular momentum about g. Therefore, I can calculate Hg by just substituting this here and subtracting from this expression, and Hg turns out to be the last expression shown here. Let us look at another problem again taken from the book of Merriam and Craig. Two spheres which are to be treated as particles of mass 1.5 kilogram each are rigidly connected to a 600 millimeter rigid rod of negligible mass and initially at rest on a smooth horizontal surface oriented along the x axis as shown. A force F along the y axis direction is suddenly applied that imparts an impulse of 10 Newton second during a negligibly short period of time. As the spheres pass the y axis aligned dashed configuration, so you can see the dashed configuration, it is aligned with the y axis. So, when the spheres pass this dashed configuration, calculate the velocity of each sphere. Now, here the problem is about a force being applied, the impulse of a force which is applied for a very short time. So, the impulse is given to us. Therefore, we use the impulse momentum relation for the center of mass of the system. The change of linear momentum of the center of mass is equal to the impulse of the force that acts on the system. If I express the linear momentum using this coordinate system, in the second just after the impulsive force has been applied, the linear momentum is indicated by g2, that is equal to mass times the velocity of the center of mass just after the impulse. So, that is mass times V x I cap plus mass times V y j cap minus the initial linear momentum which is 0 is equal to 10 j cap Newton second. It was given that the impulse of the force is 10 Newton second. Therefore, the final linear momentum of the system is equal to 10 j cap Newton second. And from here, looking at the individual components, we obtain that V x, the x velocity of the center of mass is 0, V y, which is the y velocity, y component of the velocity of center of mass is 10 by 3 meter per second. Now, we look at the angular impulse momentum relation. The change of angular momentum about the center of mass is equal to the moment, the impulse of the moment about the center of mass. Therefore, on the right hand side we have the angular impulse because of the force. Now, what is the angular momentum of the system about the center of mass? It is same as the relative angular momentum about the center of mass. So, summation of r I cross m I r I dot. And here we have two mass particles connected by a rigid rod or a rigid frame. Therefore, r I rho I dot is omega cross rho I, as we have discussed before. Therefore, I can substitute these expressions, these vectors for the two mass particles. For the first mass particle, this one, the position vector from the center of mass. So, center of mass is somewhere here. The position vector from the center of mass is 0.3 I cap meter, and this is in cross product with the mass times omega. So, there is some omega of the frame omega k cap, that will be of course be, this omega will be along the z axis. Therefore, omega k cap cross again rho I of the mass particle, again 0.3 I cap. This is the moment of linear momentum of this mass particle, relative linear momentum of this mass particle about the center of mass of the system. This is for the first mass, and similarly I can write for the second mass. In this case, the position vector for the second particle, this one is minus 0.3 I cap from the center of mass, this is center of mass, cross, this is the mass value, omega k cap cross once again minus 0.3 I cap. Now, if you do this calculation, that turns out to be 0.27 omega k cap kg meter square per second. Now, this is the angular momentum of this system just after the impulse has been applied, and this must be equal to, because the initial angular momentum is 0, it was at rest. So, this minus 0 must be equal to the angular impulse of the force. The angular impulse of the force can be written as the position vector cross the impulse because of the force. So, the moment arm cross the impulse because of the force. So, that will give us the angular impulse, and if you solve that, you will get the angular velocity of this system. Now, this is the angular velocity of the system. This tells us how the system will change its orientation, how the system is going to change its orientation as time progresses. And if you look at the linear momentum relation, if you look at the Newton's second law generalized to the system of particles like this, then you get the acceleration and velocity of the center of mass. It shows us how the center of mass will move, and the angular impulse momentum or the angular momentum governing dynamics, the equation governing the angular momentum will tell us how the system, this kind of a system connected by rigid frame, is going to change its orientation. Now, it changes its orientation, it has got a linear velocity as I have indicated here. The center of mass has velocity V x 0, V y 10 by 3 meter per second. Therefore, the center of mass is moving along the y axis, and it has got an angular velocity of 100 by 9 radian per second. Therefore, it is rotating, it is changing its orientation, and these two were obtained from the governing equations which follow from the generalized Newton's second law and the equation governing the change of angular momentum. Now, in the dashed position, if I consider this particle to be 1, I have indicated here this particle is particle 1, then velocity of particle 1 is velocity of center of mass plus the relative velocity about the center of mass, which is omega cross rho 1. Now, this rho 1 is this vector, and if I substitute the expressions, if I substitute the expressions of V g which I obtain from here and omega this k cap cross rho 1 vector 0.3, now j cap, this is g and this is rho 1 vector, Therefore, omega cross rho 1 vector I have written out here. If you do the calculation, you will get the velocity of mass 1 as in this form minus 10 by 3 I cap plus 10 by 3 j cap meter per second. Similarly, for particle 2 you can do the same thing. Velocity of particle 2 is velocity of center of mass plus omega cross rho 2. Now, rho 2 is this vector from the center of mass, this is the center of mass, and rho 2 is this vector, and since it is in the negative y direction. So, it is minus 0.3 j cap. So, that is what I have written out and calculated the velocity of the second particle. So, this completes this problem, and to summarize, we have looked at some problems based on the generalized Newton's second law for a system of particles and the angular momentum dynamics, which is governed by the rate of change of angular momentum equation. And this equation, if you remember, was derived starting from Newton's second law for individual particles, but finally what we obtained is an equation which gives us additional information about this system of particles. So, the generalized Newton's second law gives us how this group of particles is moving. So, in terms of the motion of center of mass of the system, and the angular momentum equation or the angular momentum dynamics, which is in terms of the rate of change of angular momentum of the system and in terms of the moment of all forces acting about a certain point. We have looked at 2 points. We have looked at the angular momentum about a fixed point in inertial space, which was O, and we have looked at the angular momentum about the center of mass of the system, and both the equations have the similar structure. The rate of change of angular momentum about O is equal to the net moment of all forces about O. For the center of mass system, the rate of change of angular momentum of the system about the center of mass is equal to the moment of all forces about the center of mass. These equations, the angular momentum dynamics equations, they tell us something about how the system is changing its orientation. It tells us something about the change of orientation of the system. So, change of so the translational behavior is given by the Newton's second law, and the orientational behavior will be given by this angular momentum dynamics equation, which we will be discussing further in the next lectures. So, with that I will close this lecture.